here recording for video project number 4. Pretty rough and ready, but hopefully it'll do the job. Let me just get everything in position. Boop. And there. Now I'm out of the way. So I'm doing just a couple quick little session here on some integral formulas that I think are pretty cool. Arc length I think is probably the coolest one, even though it doesn't seem that super complicated. And this is sort of the generic thing here. This is the seed that we kind of grow it out from. And maybe you notice it's pretty similar to, well, the Pythagorean theorem is kind of the granddaddy, but also, you may remember the distance formula from geometry. We got our our distance between 2 points is equal to x squared plus y squared inside a square root. Someone told me that's called a quadrature when you have squared things inside a square root. But of course that x squared is not really just an x squared, it's in physics we call it a delta x squared, or x2 minus x1, and y2 minus y1 of course for the y. So the arc length is really just, it's kind of the same thing, but we're not just looking for one distance from A to B, we're looking for the distance from the very first A to the very first B, and then the next one, and the next one, and the next one, and the next one, over the whole little distance. Every tiny little, we're cutting it up into tiny distances and measuring every single one of them. But of course, you can't just do that with a quadrature. That's where our friend the integral comes in. And the 0 and the 1 here don't actually mean anything. Now I wanted to get some kind of really interesting looking function. This is what I came up with at first, but I realized this is going to be too much work, especially once we start doing more stuff to it. So so I came up with something simpler, just a binomial inside of a fractional exponent. Yeah. So of course you can simplify this. These two are very similar. So you can already see like one step would be to take a square root on both sides, and then you could also do things like, well, you could divide the x squared and the y squared, or the dx and the dy. Divide out the dx squared. Of course, that makes the dy squared into a dy over dx squared, and you can then take the dx squared out because it's now by itself, so connected by only multiplication, and it becomes just a lonely dx. And for this curve, for that first crazy curve, I'm going to go from 0 to 2.5. But for this nice simple half of a parabola, I'm going to go from -6 to -4. And we can take a look real quick at what this curve looks like here in GeoGebra. It's very, very steep. That's what that 7 does for us. You can see it's already well over 100, and it's still more than, it's still like -5 or something, or -3 maybe. But anyway, it gets very big very fast, and it's not really valid below because that would be imaginary numbers. GeoGebra doesn't like that, I guess. Anyway, so we can quickly plug this all in, and I don't want to time limit here. In 19 minutes, this video is due, down to the wire. Anyway, so of course the first thing we have to do to get a dy dx to square is we have to take the derivative of our little binomial. And just power rule. We go from 7/2, we subtract 1, that's 2/2, so that goes to 5/2. 7/2 goes to the front, and since x derives to just a 1 and 7 derives to nothing, there's nothing to multiply. So we have here our dy dx, and then if we square that, if we add 1 and square it, we get 1 plus 49 over 4 x plus 7 to the 5th. That square root goes away. This is just what we see inside of our square root over here. And of course 1 is equal to 4 over 4. 49 plus 4 is 53. So we get 53 over 4 inside the square root times x plus 7 to the 5th. And we can just, these are all, connected by multiplications and divisions. So you can say 1/4 times 53 times x plus 7 to the fifth, so we can just quickly get rid of that square root, and this is what we have. And as you saw over here, of course, in order to get rid of the d on the dl, we integrate. And it's not so much to get rid of it, it's because it's to use it. We want to use it. It's going to help us take our little tiny slices of the length of the arc and put them all together, glue it into one long measurement. So we just integrate. Our L is equal to the integration of from minus 6 to minus 4, square root of 53 over 2, x plus 7 to the 5 halves. And of course, when we integrate, we took away our 53 over 2. I didn't really show the step, but I moved it to the outside of the integral because it's just a constant. And there's not really a 7 in it anymore. So since there's no 7 over something fraction to work with, we have to take away 2/7 to explain its absence. So the 2/7 comes out of our fraction, right? 7 halves times 2/7 is 1, so that's why there's nothing there. Anyway, we all know why that works. And we end up with this square root of 53 over 7, because the 2's cancel, times x plus 7 to 7 halves, going from minus 6 to minus 4. And that comes out to basically 47. Okay, of course, minus 4 plus 7 is 3, and minus 6 plus 7 is just 1. And there we go. That's our arc length of our crazy steep half parabola. And of course, part of the reason arc length is so cool is because it is key to other things, like surface area. What if we take this curve and we spin it around the axis? How big is it? I forgot to draw the curve in on this graph here, but it would go like that. Well, we need to know, it's basically circumference. If we get down to really tiny, really thin slices of our new surface, we're taking the circumference of each one and multiplying it by the thickness, just like measuring the side of a cylinder. Because it's not a cylinder, it has to be our dl, it has to be our arc length. It can't be our cylinder because, well, you can see here, this surface is angled. If we were just taking if we were just treating it like it was a plain old cylinder, we would just be looking at the change in our x value. But we're not. That wouldn't give us what we need. We need our length of that surface and all of those lengths. But it is really just measuring the circumference, and we already know that's 2 pi r. Well, what's r? Well, we already know it. You can see it here in the graph. It's ry. Well, what's ry? It's our function. It's our function again. Our x plus 7 to the 7 halves. So we just plug that in, and well, the question mark here is like, well, how do we measure just this surface of this well, we learned the term in class too. This is basically a frustum, right? It's a piece of a cone, almost, or close to one. It's actually going to have a curved surface, but if we get to a really tiny slice of it, it'll be basically just a cone. Anyway, so we get all of our dl's, and since we already calculated what dl is earlier, it's what's inside of this integral up here. We just plug that in. Our square root of 53 over 2, x plus 7 to the 5 halves, and the original function, x plus 7 to the 7 halves, and the 2 pi to make it the surface area of a frustum, and then from -6 to -4 to tell it which frustums we're going to add together. And you can just plug this all into your calculator. No one really wants to know how to do it for a lot of these, but this one's actually easy. This one's actually easy, but you could just plug it into the calculator. You'll get this number. It's a large surface. But, like I said, this one's easy. You know, square root of 53 over 2 and 2 pi, the 2's cancel. So you just get square root of 53 pi. And then you can take your x plus 7 and 7 halves and your 5 halves, and you can stick them together, and that's 12 halves. Well, that's 6. You know, square root of something to the 12th is going to be something to the 6th. And once we go and do integration of this really simple formula here. Of course, x and 7, when we derived them, neither one of them put any constants in front. No chain rule. Chain rule didn't do anything here, just a 1. But we lost our 7 again. It's gone, so we have to divide by 7 to get our 7 back. So we have this, and I checked, and it's the same answer, 7142.3 and some more stuff, but that's really simple. See, 3 to the 7th minus 1 times that. And I did a little more math on one of them to find like a nicer number, because the square root of 53 is kind of ugly. My calculator doesn't like to give me a nice value to look at. Anyway, that's my second one. And just to remind you, we're talking about this curve. So we're saying we're taking, if we just measured the thickness of one of these slices, like right here, going from like minus 5 to minus 5.5, that's only the x value is only 1/2, but the dl is like 10 or something. It's much bigger, so we have to use a dl for the surface area. We can't use dx, but we can use dx if we're looking for volume. Volume here, we're going to do this one for dessert. This is very easy. We're just going to use the same formula because I like it, actually. At first I wanted something much fancier, but this is nice. It's easy to work with and still a little bit interesting. So it's kind of the same situation, similar to the surface area, but here we're not concerned so much about the shape of the outside. We're looking for how much stuff can fit inside. We're looking for a stack of really thin disks. And the truth is, when you get thin enough, the shape of the surface doesn't really matter anymore for this calculation. So we're just using the dx here. How thick is this disk? Or, you could think of it like a cylinder. If this was the h of the height of the cylinder going this way, our x-axis was the height of the cylinder, then dx, of course, would just be really thin, infinitesimal, right? That's what the d means, infinitesimal. Well, a really thin slice of our height. So we have these really thin cylinders, and of course, the area inside. To find the volume of the cylinder, first you take the area of the end of the circle that is the end of the circle at the base or the top, the area of the circle that the cylinder is made of, and that's just pi r squared. And because we're still rotating about the x-axis, our circle, our cylinder has the center of our axis. So our r is still just going to be the y value, our function, our y equals x plus 7 to the 7 halves. It's the same thing. So we'll just do this, use the same guy again, but because it's just our r, all we have to do is square it. Could not be easier, really. Volume is just a tasty little snack compared to all the rest of these formulas. So, we're just going to use the same values again because they're nice and pretty when you work with them. So, just integrate from minus 6 to minus 4. The pi is a constant, it goes outside. The x plus 7, when we derived it, the chain rule didn't put anything on the outside, it was just a 1. So, but we're already at 7 this time. We don't need to find a 7, we need to find an 8. But there's no 8 there, so we have to divide it out. 1/8 then, x plus 7 to the 8th. And of course that 8 could go outside too. It's just a constant. So we have pi over 8, and we got our 3. Remember, minus 4 plus 7 is just 3. So our 3 to the 8th power minus 1, which is very nicely, turns out, very nicely divisible by 8. I forgot to write it down here, but 8 times 820 is equal to 3 to the 8th minus 1. And so we have just 820 pi, which is just a beautiful answer. But if you wanted to, use decimal numbers, it comes out to about 2,576.1. And really the thing about these for me that is so nice is that all these are just really special versions of the basic formulas that we learned in geometry and in trigonometry. It's all of our earlier knowledge, even going all the way back, to early basic geometry with just our Cartesian coordinates and just our straight lines and our very simple curves. It all matters. It all comes back. It's all important, even at this higher level of math. Anyway, that's all I have for you tonight. Thanks for watching my video, and maybe I'll see you around sometime.